All right, we're going to watch this video from the Scientific Click English channel. It's about space-time rotations and understanding Lorentz transformations. He's going to give us a nice overview of Lorentz transformations and how space-time works and all that. So here we go.
Welcome back to Science Click. Today, space-time rotations. We live in a geometric space in which we can move, turn, measure lengths or angles. Each person has their own frame of reference, a unique point of view of the universe, of which we are the center,
and I know, right? Very clean.
through which we locate objects around us. Taking this person's frame of reference, for example, the car is moving. But in the driver's frame of reference, it is the person on looking which moves. Frames of reference describe the universe from a given point of view. 3 axes are enough: left, right, up, down, forward, backward. At the beginning of the 20th century, this paradigm was turned on its head when we understood that time is actually a fourth dimension of the universe. There is a fourth axis, which must be taken into account. In this video, we will try to explain this revolution, which has since allowed scientists to unify space and time, but also the electric and magnetic fields, or momentum and energy. Let's imagine a street in which a person A is standing on the sidewalk and a person B is driving a car. The car moves forwards relative to the street, and to describe its motion, we will construct a space-time diagram. To do this, we freeze each instant and stack the images on top of one another. They thus form a block which represents the flow of time. In this block, the 2 persons move towards the future, each drawing their own world line. Person A follows a straight line towards the future, while person B, who is moving, traces a tilted path. Each slice of the diagram pinpoints their location at a given time. At this stage, the situation is described from the point of view of the road in the reference frame of person A. What would the diagram look like if we asked the driver to draw it from his point of view? In his reference frame, B is at the center of the universe. To form his diagram, we must therefore shift all slices one after the other to replace him at the center of the scene. The car is now motionless, and it is person A who seems to be moving backwards. We have just performed a Galilean transformation. Shifting the slices of space allows us to change our frame of reference. In this way, physicists understood as early as the 17th century that motion depends on the observer. For A, B is in motion, but for B, it is A who moves.
Yeah, dude. It's when you see this, and when I think he covers Minkowski space-time in this too, it'll make a lot of sense with the light cone graphics and how they present it with the, with the idea that they've added this fourth dimension of time to it. Okay, you can kind of see what they're doing with it. Obviously it's an abstract concept, but it is very cool. Regardless.
Neither of these 2 statements is more valid than the other. Motion is relative. If B decides to throw a ball, the speed of the ball will seem faster for A since it is moving with the car. According to Galileo, we can add up velocities to change reference frames. While this idea may seem natural and intuitive, a discovery made at the dawn of the 20th century came to question it all. Imagine that A and B both turn on a flashlight. Neglecting the presence of the air, which slows it down, light escapes from the 2 lamps at 299,792,458 meters per second. Viewed from the road, we would expect that the ray launched by B moves slightly faster since it should add to the motion of the car. However, against all expectations, the 2 beams have exactly the same speed. With astonishment, physicists discovered that this precise speed is absolute. Any object moving at 299,792,458 meters per second will have this exact speed in all reference frames. It is called the speed of light.
So, keep in mind. So, this is setting the stage for the coordinate systems and how they extrapolate that the coordinate system conforms to the speed. So they take this fixed thing and they say in any reference frame, right? So the way that they've determined that through the Michelson-Morley, right? This is a 2-way speed measurement. So the light hits the mirror and reflects back. So what they're assuming, though, from that is that the speed of light going there was the same speed and the speed of light coming back was the same speed. But obviously, what produced the French pattern was from the arms that were facing east to west. So when that French pattern was produced out of that, that's what showed that this speed that they're saying is the same in all reference frames isn't actually the same. But when they chalk it down to a null result, that's where they're able to come in and act like this is a fixed speed and apply this whole interpretation and coordinate system based on that, and as long as everything transforms covariantly, where C remains the same, like they're good to go. And obviously the other laws of physics, but
Right.
primarily
So
concerned with this because this is their measuring stick between events.
So they could probably, or then he's not going to go into this, but what I immediately thought of was the covariance scaling problem. When you use a metric like this as universal, the speed of light C, and you transfer it to a coordinate system, then all of a sudden C is a different value, and you're like, hey, wait a second, I thought it was invariant in all coordinate systems except for the one that it's not meant for. Then you got to do a bunch of adjustments, I guess. But that's cool.
No, exactly. That's exactly what's going on with GPS. So when I was first bringing this up on Earth Awakening server, and Dogs was asking me like, well, isn't this a one-way measurement? Like, so isn't the speed allowed to change in that reference frame? No, it's assumed to be the same in all reference frames, even in a one-way situation. And that's exactly what's producing the discrepancy because GPS is so accurate, or they have the time interval so like down to such a precise degree that they're actually like it's showing that this broad what is it like this like general approximation of how fast it is, which is like good enough for most stuff. But when you try and derive a distance from it using a time interval system, and if you get real specific with it, like it starts showing that there's variance to it to the degree where it's not only just an ether wind, that's actually the delay in time is proportional to the velocity of the observer. So I don't think he covers it in this video, but he should. I think he might reference it, but he says like the speed of light, shouldn't change for the observer in motion either. But obviously through GPS it does, and through laser interferometry it does. But these people all think that it's fixed or whatever. But yeah, so
right.
we all caught up or ready to continue?
Moving on.
All right.
This finding came as a drastic shock. How is it possible that this speed does not add up to that of the car? Why, unlike the ball thrown by B earlier, does light not change speed from one frame to another? To grasp the extent of the problem, imagine that A emits one light ray on each side. In her reference frame, both rays have the same speed. But in B's reference frame, the diagram becomes slanted. For him, light should move faster in one direction than the other, and yet it remains the same. The solution to this paradox will be found at the beginning of the 20th century. For the speed of light to remain constant in accordance with observations, the diagram must be distorted by shifting not only slices of space, but also slices of time. This manipulation is the only one allowing us to change reference frame while preserving the speed of light in both directions, and without distorting either straight lines or the volumes of the diagram. We call this a Lorentz transformation. The idea behind it is shocking. Time and space warp and change direction depending on the observer.
So time and space change depending on direction of the observer, right? So, as if like, I don't know, the ether wind affects propagation depending on the direction of the observer, right? So they literally just reverse engineer the effects of that and said that the coordinate system contracts or expands, in regards to compensate for the change. And another thing to note there is, so how when Whitsitt has made the point that like, for time and or for them to length contract, they have, when they change the distance, they also have to change the time because they're intertwined, and people try to argue against that for some reason. Even though that's it's
right.
it's pretty obvious. It's like this lays it out so concisely and clearly. Like I really like this video because it just like he just says it like it is what it is. It's exactly how it works. Like it's not
like you'd expect it to vary, but it doesn't. So we'll just bend all of reality around this thing so that it doesn't anymore, and then our tenant is unfettered. You're like, whoa, dude.
He's like, whoa, yep. And so keep in mind, like. The bending and warping and contracting and all this stuff is dependent on a fixed speed of C. If C is not the same in any frame, then none of this applies. It's all physically vacuous, as they say.
Between events, the order in which they occur, and even the lengths of objects become relative measurements, which change from one point of view to another. These two events, for instance, occur 1 second apart in this first frame, but 1.1 seconds apart in this other frame. And the car is 4 meters long in its own frame, but slightly shorter in the frame of the road. When a body moves relative to us, its clock seems to tick in slow motion, and its length seems contracted. This is special relativity. Let's slightly digress for one moment. Viewed from above, a city can be depicted on a map that identifies the layout of its road network. If we rotate this map, the position and direction of the roads seem to change. This is just an illusion. The orientation of the map is arbitrary. It is an abstract description of the world which does not impact reality. Physicists quickly made the analogy between the space-time diagram and the map. Like a map, our diagram is only an abstract representation of the universe, and like with a map, we can change our point of view to look at it. In other words, the Lorentz transformations which allow us to switch reference frames are somewhat equivalent to the rotations of our map. This idea makes sense because, like rotations, Lorentz transformations preserve straight lines and volumes. But unlike classic rotations, Lorentz transformations seem to distort the diagram. They do not preserve distances between points. Some move away, while others get closer. And while rotations draw circles, they draw hyperbolas. How could such transformations be equivalent to rotations? The genius idea to explain this will be brought by Poincaré and Minkowski. They invented a new way of measuring distances within the diagram, the Minkowski metric. According to them, our diagram is abstract and does not faithfully represent real distances through spacetime, somewhat like a world map which deforms the surface of the Earth to make it flat. Even though it may not look like it, all the points which make up a hyperbola would actually be the same distance from the center. The hyperbola would be the analog of a circle, the curve whose points are all the same distance from the center. By changing frame of reference, all points slide along these hyperbolas while remaining at the same distance from the center. Thanks to the Minkowski metric, the analogy becomes perfect, and the Lorentz transformations are indeed analogous to rotations. They are hyperbolic rotations. Unlike a classic rotation, which can turn in all directions, a hyperbolic rotation distinguishes two types of directions. On the one hand, durations, which can be brought onto the time axis, and on the other hand, lengths, which can be brought onto the space axis. Durations and lengths are intervals of a different nature, intervals of time or of space, and light rays form a cone which separates them fundamentally. Whatever the frame of reference, a duration remains a duration, and a length remains a length. Hence, since each observer advances towards their own future, it is impossible to go back in time. We are confined within these light cones, and in all frames of reference, the future remains the future. A classic rotation always ends up looping on itself after 360 degrees. But a hyperbolic rotation can rotate indefinitely, because the angle of the rotation is no longer measured along a circle, but along a hyperbola which extends to infinity. We can thus rotate spacetime as much as we want. The angle of a spacetime rotation is called rapidity. It measures how fast one frame of reference moves relative to another. The rapidity of the car, for instance, is the angle between its own frame and that of the road. If the car accelerates, its rapidity increases. If it accelerates for an infinitely long time, it would end up reaching the speed of light. Thus, the speed of light actually amounts to an infinite rapidity. It is the maximum speed that an object could only reach in theory when accelerating for an infinitely long time. Light is infinitely fast. When B throws a ball, it is not its velocity or its speed which are added to that of the vehicle, but its rapidity. Thus, when B emits light, the speed of the car does not add on, since the rapidity of light is already infinite. By revealing all these concepts, physicists have gradually discovered the geometry of spacetime. Far from being an abstract diagram, spacetime is now a physical entity, endowed with distances and rotations.
So, from this, like, you see how they've taken the algebraic concepts of contracting the system and all that, and then put it on in terms of geometry, where they've attributed the effects to following like the path of a hyperbola.
Yeah, and they attributed it to a physical thing, and now it's no longer an abstract concept. It is absolute physicality, which is weird.
So well, the interesting thing with the physical entity part of this, right, is like, so if it's a physical entity, then it's responsible for things like wave compression and like the Doppler effect. So it has a way to facilitate an energy transfer mechanism to produce the effects that they say, make it a physical entity. And, obviously we know from how math became reality, none of those experiments, pan the way of proving that for them. So this is still just abstract, concepts that they've applied to a coordinate system to make it appear covariant, or, to give a covariance through adding geometric properties to something that's not even physical, but then saying that it folds in on itself to maintain the illusion of, like it's going forward in time, and an event that happens here can be the cause of an event that happens over here, as long as it's within the confines of the coordinate system. All right.
New vision has allowed scientists to understand that time and space are only dimensions of a single object, spacetime. Spacetime allows us to better understand the notion of acceleration, for instance. An object is said to accelerate when its motion is altered by changing either speed or direction. In spacetime, we understand that these two cases are both rotations, a classical rotation or a hyperbolic rotation. Accelerating actually amounts to turning within spacetime. Spacetime also unifies electric and magnetic fields.
So real quick to go back to, well, I don't have to go back, but let's see where we at, 12, 14. So to go back to here, so like an observer in motion, right? Like that's how they're plotting that. So when you're accelerating, you're experiencing the curvature of space-time. Your geodesic path is altered by your energy. It's conforming space-time around you, that sort of shit. Like that's what they're all talking about with that.
Yeah, that picture right there. He says when you're actually accelerating means you're actually doing a curve. You're accelerating hyperbolically in geometric space-time, which actually amounts to the same. Yeah.
Yep.
I mean, dude, I get it, but it's a crazy application. Like at the end, we'll have to go through it.
Yeah.
Hyperbolic rotation. Accelerating actually amounts to turning within spacetime. Spacetime also unifies electric and magnetic fields. An electric field generates a force which accelerates charged particles, while a magnetic field generates a force that makes them turn. These two situations are in fact analogous. Just like the magnetic field, the electric field makes particles turn, only with hyperbolic rotations within spacetime. The electric field.
Now the thing with this though, there has to be charge potential between them though, so that otherwise this electric field can induce the magnetic field. Now this was changed in Maxwell's equations, or this is what Maxwell changed to the so-called Maxwell's equations, which is a set of, I think it's like 4 equations of the laws of electrodynamics and all that. So what he did there was just remove the need for there to be something to carry the charge potential for these two, for the moving electric field to induce a magnetic field, and then the magnetic field induces the electric field. So yeah, just throwing that in there for continuity or whatever.
Removing the ether and the energetic background to which things propagate, and then just asserting that this can propagate itself indefinitely in perpetuity with no backing. Got it?
Yeah, cool. Indeed. Yep.
Field is the time version of the magnetic field. Finally, this vision allows us to unify the notions of momentum and energy. Energy is actually the time version of momentum. While one measures movement through space, the other measures movement through time. A stationary object, for example, has no momentum. It does not move through space, but it has energy because it moves through time towards the future. If the object accelerates, its speed changes. It turns within spacetime and gains both momentum and energy. By approaching
just starts curving, dude.
These two quantities tend to infinity. Lorentz transformations are only abstract rotations of our map of the universe, changes of reference frame which don't affect the true geometry of spacetime. In the years following these breakthroughs, Einstein and his contemporaries will discover that spacetime can in fact get distorted, explaining the phenomenon of gravity. The theory of general relativity is born. However, special relativity was not abandoned for all that. Just like the Earth, which is curved but seems flat on a small scale, spacetime is still adequately described on a small scale by the Minkowski metric, the basis of our understanding of the universe. Today, new theories are trying to understand this geometry at the fundamental scale. Is spacetime perfectly smooth, or rather cut up into small grains? Does it include more dimensions which could be curled up and therefore invisible at our scale? Or maybe it fluctuates with quantum agitations. Ideas and theories abound in the hope of one day achieving.
See, like they've skipped so far past, dude, like after all that, it's like we got it narrowed down to maybe it's perfectly smooth, maybe it's a little rigid, maybe it's chunked up, diced up space-time, Shane. Like imagine you have a jar of space-time and it's just a bunch of little space-time particles and you shake it up and you'd like a fucking snow globe.
Dude, how dare you? How dare you elegantly and eloquently use a mathematical description to bamboozle the sheeple into believing this is reality? Like, how fucking dare you?
How dare you? All right.
Achieving a fundamental understanding of the universe.
Oh
yeah, it's almost over, boys.
It hurts.
All right, that's good. We're good. So yeah, fundamental understanding of the universe.
I see why you like it though. I mean, it has a good visual depiction of the mathematical concept that they used to convince people that math was reality.
Yeah, it really catches you up to date if you're not familiar with the subject matter, because it accurately portrays like what they actually say about it, and how it works. So very cool. So do you have any thoughts on the video or anything like that?
Oscar, what do you think?
I think it's so far over my head, I don't even understand it. But I think even if I understood it, I still wouldn't understand it.
Indubitably.
That's pretty eloquent.
It
All right.
sounds like it's just like weird philosophical stuff, basically.
Yeah, that's
Well,
basically what it is. It's philosophy written in mathematics, and then they just tell everyone that it's actually a true physical entity.
I like how he said with like such confidence that we can use this because the speed of light never varies in any coordinate system, no matter what. And we just went through a presentation where it did exactly that, and it caused all these problems, and it generates things like the Sagnac effect, where they have to specifically accommodate for, and there's like published papers on the different interpretations over why they think that is, and because it violates the special principles of relativity that he just laid down as concrete. It's like a big like logical circle jerk almost.
Yeah, it's one of the biggest, like, once you realize like the interferometry stuff shows a varying speed and GPS shows a varying speed, and it's like, oh, so you guys based everything on a speed distance that, you know, varies, and you guys say it doesn't vary, and then your mathematics explicitly works on like a non-varying speed, and you know, that's a
Yeah,
problem.
he said it. He's like, "Oh, this is a tenant. Like we know that it doesn't, and it can't because we're doing this." And it's like, "Oh, but
Yeah.
what about all those instances where it does? Doesn't that violate? Like it's kind of like the black sheep thing. If one specific instance violates, then it doesn't work, and we can think of dozens where it won't."
Yeah, and that's the crux of it, right? Because they've turned around and used the presupposition of invariant C as, you know, the justification for length contraction, time dilation, different reference frames that capitulate to the invariant speed of C that isn't real. So you could never but as long as that happens, like, or as long as the transformation is invariant, like they take that as like, you know, they're in alignment with physics, but like it's not, because in the one reference frame it can be measured in, it's varying on the one-way speed and the two-way. So
Right, and when you try to transfer that in varying speed to a different coordinate system, you have to make a whole bunch of adjustments that you wouldn't need to do specifically if it was as constant as you pretend it is.
yep,
Crazy.
they wouldn't have to leave the ECI frame, so they could just take the range measurement equation and use it in the ECF frame. But because all the axes of that coordinate system are in rotation, it's a relative motion reference frame. The ECI frame, you know, with that stationary position, applies for relative motion to be measured against some, you know, the stationary non-rotation. So I think that's the crux of it right there.
Yeah, that's the reason why it
It's
works there
one
mathematically,
one
conceptually.
yeah, all motion is not relative.
Mm.
There's absolute. So all right, that's the end of that video, end of the commentary. I think all the interesting points I wanted to bring up on that I can think of. Any final thoughts?
No, it was fun.
All right, cool. I'm going to close it out and upload it immediately.